In this video, we're going to be testing the claim about a standard deviation using the critical region method. To do this, we're going to need to know the test statistic formula, which is chi-squared equals n minus 1 times s squared over sigma squared. And what each part means is over here. Don't forget, we need to know what the degrees of freedom are when we're testing the claim about a standard deviation. So let's look at the example. Tests at a college's elementary statistics classes have scores with a standard deviation equal to 14.1. In one class, there were 27 test scores with a standard deviation of 9.3. Use a 0.01 significance level to test the claim that this class has less variation than the other classes. Does a lower standard deviation suggest that the last class is doing better? So we're going to start off by writing our hypothesis, so our null. And since we're dealing with a standard deviation, we use sigma, and it's going to be equal to test the claim that this class has less variation than the other classes. And we know that the population standard deviation of this college's elementary stats classes is equal to 14.1. So sigma is going to be 14.1. And the alternative, sigma, is less variation, so less than 14.1. We have an alpha value, a significance level of 0.01. We also know that our n value is 27, so that means our degrees of freedom is 26, and s equals 9.3. So now that we have this, we're going to go in and find our critical value, but to do that, since it's a left tail test, we're going to take our alpha value of 0.01, and we're going to do 1 minus 0.01 to get 0.99. And from that, we'll find our critical value. Now to do that, we're going to go into our chi-squared table and look for 0.99, where our degrees of freedom is 26. So here's our chi-squared distribution table, and this will be the graph that we use to find out whether we reject or fail to reject. It won't look exactly like this, but it'll be pretty close. So we're looking for degrees of freedom being 26, which is right here. And we're also looking for 0.99, which is going to be right here. So where do they match up? Match up right there at 12.198. So our critical value is going to be 12.198. And now we need to find our test statistic. So we use our formula up here. So our t-stat is going to come from chi-squared equals n minus 1, which is our degrees of freedom. So we'll say 26 times s squared, so that's 9.3 squared, over our sigma squared, which is 14.1. And when we do the arithmetic here, we're going to get to 3 decimal places, 11.311. So now we have our critical value, and we have our test statistic, and so now we're going to do our little graph to see whether we reject or fail to reject. So right here. So we get 0 here, so our critical value is 12.198. So we'll say it's right here. And since it's a left-tailed test, we are shading to the left. And our critical value of 11.311, our test stat. So 11.311 is going to be, we'll say right here. And that is within the rejection region. So in rejection region. So that means we will reject the null hypothesis. So we know what we're going to be doing, but we still got to answer our question, which is testing the claim, and then does a lower standard deviation suggest that this last class is doing better than the other ones? So I'm going to go in here and write out our conclusion. So since we reject the null hypothesis, we can say that there is sufficient evidence to support the claim that this class has less variation. Now, it also asks up here, does the lower standard deviation suggest that this last class is doing better? Well, we know that there's less variation, but it doesn't mean that there's less variation on the good side. It could be less variation on the bad side. It could be all doing bad. There's not enough information to say that. All we know is that they're kind of grouped together. So what we could say is that the lower variation implies that the scores are closer together, but it doesn't imply that the scores are better. There could be less variation and they're all failing, or it could be less variation because they're all getting A's. We don't know. All we know is that the scores are more tightly compacted. So here we go for this one. Everything in one nice little snapshot for testing the claim of a standard deviation.